Good morning, I hope you're all well. This is a video, the third one in fact, on equations and inequalities. The main focus of today is going to be just finalising the relationship between graphical solutions and algebraic solutions. From GCSE you will have seen time and time again how we can graph equations, even quadratic and above, and where they intersect relates to the algebraic solutions of those equations, simultaneous equations. It's very unlikely, I will say, incredibly unlikely in fact, that for A-level you'll be asked to plot graphs. I don't really foresee that happening in terms of solving simultaneous equations by graphing. There might be a tiny bit on that in a different sort of way the question is explained, but in terms of do a table of values and plot, like you might have seen for GCSE, I'd say pretty much no chance. So the main thing of today is just to get your head into the concept of a link between the actual algebra and the graphical sort of visual approach. But as I say, this isn't going to be a main focus for the A-level per se. Before we crack on, there's 4 warm-up questions for you to have a go on. Questions 1, 2, 3, 4, obviously. So try these, and then check your solutions using the video if you need to. Don't just use the video to copy down the answers. That way you'll learn nothing. So let's have a look together, talking through the solution to question 1. So for question 1, we have this fraction which involves a third root 5, and we need to express this in the form a plus b root 5, where a and b are integers. The key thing here is to realise that if we need to express it in this form, we've got rid of any denominator, and so this is a test of remembering, can you rationalise the denominator? So what we do for that, to rationalise the denominator, is we have to multiply both sides, top and bottom, by this denominator with the sign swapped. And so the 3 plus root 5 needs to become 3 minus root 5. So multiplying top and bottom by this, for the first step. So on the bottom we're going to end up with 3 squared minus root 5 squared. This is effectively just the difference of 2 squares. So 3 times 3 is 9. Root 5 all squared is just going to be 5. So it's going to be 9 minus 5. This top we're going to be expanding out brackets. So 7 times 3 would give us 21. 7 times minus root 5 gives us minus 7 root 5. Root 5 multiplied by 3 will give us positive 3 root 5. And then root 5 multiplied by minus root 5 will be minus 5. All of that over 9 minus 5. And 9 minus 5 is obviously going to be 4. So let's neaten up the top. So 21 minus 5, that's going to give us 16. Minus 7 root 5 plus 3 root 5 is going to be minus 4 root 5 overall. We can now divide everything by 4. And so 16 divided by 4 gives us 4. Minus 4 root 5 divided by 4 just leaves us with root 5. And so that's question 1 done. So in our case, a is 4 and b is negative 1. For part 2, we need to simplify 16x to the 12, all of that to the power 3/4. There's a few ways of tackling this. What I'd suggest is we can think of 3/4 as 1/4 times 3. And so we can do the root first. We can do the 4th root of this, and then do the power 3 after. And so it can be considered as 16x to the 12. The 4th root of that, all to the power 3. Now I've chosen to do the 4th root because these here have 4th roots which are easy to see. So for example, the 4th root of 16 is going to be 2, because 2 times 2 times 2 times 2 gives us 16. And we can find the 4th root of x to the power 12, because 12 divides by 4. So this is going to become x cubed. And so if we take the 4th root of all of this, we'd get 2x cubed. and then we take that to the power 3. So 2 cubed is going to be 8. X cubed will become x to the power 9. Question 3. 2 parts to this one. So we have this expression, x squared minus 8x minus 29, and we need to rewrite it in this completed square form, where a and b are constants. So to find the value of a and the value of b, what we need to do is complete the square, and then compare our values to the positions of a and b. So let's just do that now. So x squared minus 8x. So in the brackets we'd put the x minus 8 we can just rewrite as minus 4. Remember, we always half the coefficient of the x. And square this, and subtract off the minus 4 all squared. Minus 4 all squared is positive 16, so we subtract away 16, then minus off 29. Then neaten this up, we get x minus 4 all squared. Minus 16 minus 29 overall is negative 45. So we can see here how the a and b relate, and so here the a is going to be negative 4, and the b we've got is minus 45. So therefore a is negative 4 and b is negative 45. There's nothing here that says a and b have to be positive, so that is allowed. For part b, it says hence or otherwise show that the roots of this equation here are c plus or minus d root 5, where c and d are integers to be found. So what we've done here for part a is we've rewrote this in this form. And the clue here, it says hence or otherwise. So otherwise means you don't have to, but hence means part A can help you. So using part A, we can solve part B. And so instead of using this form here, equals 0, what we can do is use this completed square form. And so what I'm going to do here, I shall put this in black, not in red, we'd have x minus 4 all squared minus 45 equals 0. Now we can add 45 to both sides to get x minus 4 all squared equals 45. Then if we square root both sides, we obtain x minus 4 must be plus or minus the square root of 45. However, 45 has a factor which is a square number, and I'm not talking about just 1 itself. So 45 has a factor of 9. So root 45 is the same as root 9 root 5. But root 9 is 3. So we can rewrite this as plus or minus 3 lots of root 5. Then by adding 4 to both sides, we see that x is going to be either 4 minus 3 root 5. So that's one solution we've got. Or it could be that x equals 4 plus 3 root 5. And so that's the second solution. So in this case, C is 4 and D is 3. For question 4, we've got this equation here, and it says P is a positive constant, so important P is positive here, and it has equal roots. And so it's a quadratic equation, and we're told about the roots. So we need to recall what particular property of a quadratic tells us about the number of roots, whether it be equal roots, 2 distinct roots, or no roots. It's a question about the discriminant. Okay, so what we need to do here is remember that equal roots means that the discriminant, this triangle symbol, which I can rewrite for you here in case you've forgotten what it means with discriminant, must be equal to 0. If discriminant's greater than 0, it's 2 distinct roots. If a discriminant is equal to 0, that's equal roots, in other words, a repeated root. And if a discriminant is less than 0, we have no real roots. And so now we need to remind ourselves what the discriminant actually is. Well, in the standard form of quadratic, ax squared plus bx plus c equals 0, the discriminant is b squared minus 4ac, where a is the coefficient of x squared, b is a coefficient of x, c is a constant term on its own. So let's just map a, b and c to what we have here. And so a, the coefficient of x squared, well, there's nothing in front of the x squared. In other words, you just have 1 x squared. For b, the coefficient of x, we've got 2p. And the constant term at the end, c, is 3p plus 4. And so we just chuck these terms in for b, a and c and solve. So b squared is 2p squared, and minus 4 times 1 times c, which is 3p plus 4, equals 0. So let's expand this and neaten it up. So 2p squared is 4p squared. 4 times 1 is just 4, so it's 4 lots of this bracket. 4 times 3p is 12p, so minus 12p, because of this minus 4 times 1. And then we've got minus 4 expanded out with the 4. 4 times 4 is 16. So we have minus 16 equals 0. Now before we try and factorise this with all these terms, have a look at the coefficients here. All these numbers can be divided by 4. And so if we divide through the whole thing by 4, we obtain p squared minus 3p minus 4 equals 0. So this can now be factorised. We can put this into brackets and have p plus 1, p minus 4 equals 0. At this point, remember what the question said. P has to be a positive constant, okay? So normally here we'd say p can be minus 1 or p can be 4, but because p is defined as being positive, we have to ignore the minus 1 option and say that p must be equal to 4. And for part B, it says for this value of p, solve the equation x squared plus 2px plus 3p plus 4 equals 0. So we can substitute in now that p equals 4. So x squared just stays as x squared. 2p must be 8. And 3p plus 4 becomes 3 times 4, which is 12, plus 4, which is 16. Hence, we're solving this. So again, we can think of two numbers that multiply together to give us 16, and when we add them give us 8. That's 4 and 4. And so this is going to be x plus 4, brackets x plus 4, equals 0. In other words, x plus 4 squared equals 0. Therefore, this only has one root, which we'd expect, equal roots, when x is equal to minus 4. And that's for one and only repeated solution. Next up, I'm just going to jump straight into this idea of graphing simultaneous equations and where the intersections come. That relates to the algebraic solutions. So we've got two different equations here to solve simultaneously. 2x plus 3y equals 8 and 3x minus y equals 23. And so what we can do here is graph both of these. Okay? And where they intersect, that's going to be the solution to these equations. If you want to, like at GCSE, you could just do a table of values for these. That's absolutely fine. What I'm going to do is just think of picking any 2 points on the line and then doing a straight line through them. And that will show us what the line representing the equation must be. And so, for example, if I were to pick x being, let's say, if x was if x was 4, okay, for example, if x was 4, 2 times 4 is 8, and so y would have to be 0, and so 4 and 0 is a point on this curve. I'll say curve, I mean straight line. So let's just put this in. So this one is going to have a point here which it's going to go through. So another thing we could say is, let's say if x were minus 2, 2x would be minus 4. So 3y would have to be 12 to make this equal to 8. So 3y would have to be 12, y would have to be 4. And so minus 2 and 4 must be another point on this line. Then what we can do is just do a straight line through these points and extend it if needed, which I can do here. So that's the first one done. So I'll just put a line here to say this one denotes this line. The second one, 3x minus y equals 23, what I'm going to do here for this one, I'm going to rearrange that to the standard y equals mx plus c form. So we get y equals 3x minus 23. And so the y-axis intercept is going to be way down at minus 23, way off this graph. And so because it's got a positive gradient, it's going to come up at some point, but it's going to come up further on. So I'm just going to pick when x is 8, for example. And so if I add when x is 8, 3 times 8 is going to be 24, minus 23, that's going to be 1. And so when x is 8, y is 1. If x was 6, 3 times 6 is 18, minus 23 would be minus 5. And so 6 and minus 5 would be a point as well. So we can see already that it's not going to be on this page for long. It's just going to be at the last quarter or so of this graph. So if we were to now just draw a line representing that, going through these 2 points, remember for a straight line graph all you need is 2 points, you know. That one would look something like this. So now we can see that we've got 2 different lines representing these 2 different equations, the green and the blue. Where they cross, that's going to represent the solution to these simultaneous equations. So we can see here they cross at a particular point where x is 7 and y is minus 2. They intersect here. Okay, and from that, okay, we can therefore deduce that the solution to these simultaneous equations is when x is 7 and y equals minus 2. Now, question 2, we've got a linear equation and a quadratic. And so this is going to be slightly trickier, but yet something we can do quite easily at the same time. So what I'm going to do first of all is try to graph 2x plus y equals 3. And so I'm going to rearrange this to y equals minus 2x plus 3. And so using the idea of y equals mx plus c, the y-axis intercept is going to be at 3, and it's going to have a gradient of negative 2. So it's going to be going down by 2 every time x is going along by 1. So we're going to have a line looking something like this. And all we need is a straight line going through these points, like so. And so that's the graph of y equals minus 2x plus 3. In other words, the graph of 2x plus y equals 3. For this one here, y equals x squared minus 3x plus 1, that doesn't factorize. And as well as that, as you've seen with me, maybe you're the same, I'd imagine you might be better, to actually draw this curve accurately, where it goes through the appropriate points, can be hard. And so if you want to graph a quadratic, it might well be an idea to do a table of values, just so you know that your curve's going to go through the correct points and not miss them. So I'll leave this one on here, and now I'm going to just add in a table of values for this quadratic. So if I just label this one here as 2x plus y equals 3, we can do a table of values for y equals x squared minus 3x plus 1. And so we can use a calculator for this. In fact, I'd recommend you do that. But in case you just want to follow me and trust me, x squared, when x is minus 3, x squared is 9, then minus 3 times minus 3 is 9 plus 9, which is 18, plus 1, that's going to give us 19. When x is minus 2 all squared is 4, 3 times minus 2 is minus 6, so minus 6 is plus 6. 4 plus 6 is 10, plus that 1 is 11. When x is minus 1, x squared is 1, 3x is minus 3, so 1 minus minus 3 is 4, plus 1 is 5. When x is 0, dead easy, 0, 0, just 1. When x is 1, 1 take away 3, plus 1, that's going to give us minus 1. When x is 2, 2 squared is 4, minus 3 times 2 is 6, 4 take 6 is minus 2, minus 2 plus 1 gives us minus 1 again. When x is 3, 3 squared is 9, minus 3 times 3, 9 again, 9 take 9 is 0, plus 1, we have 1. Now we can use the symmetry of quadratic coordinates to help us. You can see the y values are repeated here, so there's going to be symmetry around here. So if they're minus 1, these are going to be 1, the next one will be 5, and the final one will be 11. So we can now plot this. So minus 3, 19 is way off the page, as is minus 2 and 11. But minus 1 and 5 we can add on. 0 and 1, 1 and minus 1, 2 and minus 1, 3 and 1, 4 and 5. So if we just plot it through here. Now, as I say, I can't really plot these for toffee, but I'm going to have a go. Whoops. Whoa. That happened there. So yeah, as I was saying, I'm absolutely awful with this. I'll keep it on just so you can laugh at me in class. Free that one. Free that one. Dips and back up. And finally there. Oh, that was a challenge. So now we can just label this y equals x squared minus 3x plus 1. And you can see, in fact you probably saw before I plotted it, and put on the curve that it intercepts twice. So here and there. So we can now see the solutions relating to these pair of intersections. So therefore we have x is minus 1 and y is 5. And the other one is that x is 2 and y is minus 1. For part B, though, we need to verify this algebraically. So for part B, what we need to do is show this using algebra. And so if I have a look at this top equation here, 2x plus y equals 3, we could rearrange this to say y equals 3 minus 2x. So in other words, what we can do here is we can substitute in 3 minus 2x in place of y. So that's what we're going to do. So sub 3 minus 2x for y. So this bottom quadratic, instead of putting y equals, we can put 3 minus 2x, because that is y. So 3 minus 2x equals x squared minus 3x plus 1. We can rearrange this. If we add 2x to both sides, we get x squared minus x, then minus 3 from both sides, we get minus 2 equals 0. This now factorizes. We can say that's the same as x plus 1, x minus 2 equals 0. And we can see clearly now that this is going to have roots where x is equal to minus 1 from the first bracket, or from the second bracket, x is equal to 2. So now we consider both cases separately to work out the corresponding values for y. So let's just think about when x is equal to minus 1. We can use this equation here for y. So when x is equal to minus 1, y is going to be 3 minus 2 lots of minus 1. 2 lots of minus 1 is minus 2. So y is going to be 3 minus minus 2. In other words, 3 plus 2, which is 5. In other words, when x is minus 1, y is going to be 5. So that's one solution pair. We can now do the similar idea, the same idea in fact, for when x is equal to 2. So let's just try that. So when x is equal to 2, using the same equation again, this one here, y is going to be 3 minus 2 lots of 2, which is 1. And so, in other words, when x is 2, we have that y must be, sorry, minus 1. 3 minus 2 times 2. 3 minus 4 is minus 1. What am I on about? Bloody useless. Forgive my silliness. There we go. So that's the second pair of solutions, which I'll just highlight in yellow again for no reason whatsoever. I like that yellow, so there. So that's all there is to it really. So when you try these exercises on page 45, just try questions 3 through to 9. Now it does say to sketch. I want the emphasis to be on solving these algebraically, okay? So don't bother plotting them. So for questions 3 through to question 9, focus on the algebra, focus on the mastery of the algebra, and then sketch after, just so you can see the link between the visual and the abstract. So don't treat this as like doing a table of values and working it out step by step. I may have shown you that there, but that's all I really want you to focus on. Try and master the algebra here. So have a go at those, same drill as ever, check your answers on the back. If you've not got the same, try and find out where you've gone wrong. If you're not sure, ask me or a classmate. Thanks again for listening, and I'll see you again soon.